right, hello everyone. So this is the second video of section 1.3. In this video, we're going to introduce a few algebraic properties of vectors, most of which I think are fairly intuitive. And what I mean by that is that if we were to work with, vector addition and scalar multiplication more, you would probably use some of these properties intuitively without even really thinking, about it. Because I think most of these properties are just properties that are inherently true about normal addition and multiplication in general. But it's good to state them and sort of just go over them and verify that we can use these properties when working with vectors. So first off, I want to just go over a couple things. So first thing, if U is a vector in Rn, and remember that means that U is a vector of length n, we will sometimes use shorthand notation to write that, and we will instead write this to mean that U is in Rn. And this symbol that sort of looks like a, kind of like an E or maybe an epsilon. So this symbol here is meant to be read as is in. So this sequence of symbols here would read U is in Rn. And so you'll see me use that quite frequently here moving forward because it's sort of just an easier, more compact way to express this, and it tends to make things easier moving, when we're working with a lot of vectors and vector spaces and things like this. So another thing, sometimes we'll use this notation as a general way of expressing U. Often when working with vectors, we want to be as general as possible. And so notice here, this allows me to specify a vector and specify the entries of a vector without definitively defining what those entries are or how long the vector is. So notice here, this is a vector of length n. It has n entries that I'm just denoting by the variables u1 through un. And last but not least, I think I promised this definition in video 1, but I wanted to make good on that promise. The zero vector in Rn is just the vector of length n that contains only 0 entries. Now, you might be a little peeved at the ambiguity of this definition, right? Because the zero vector in Rn is denoted by 0 with an arrow over it and equal to this vector of length of all zeros. And notice that I haven't in anywhere in this definition specified exactly how long it is. The length of the zero vector will generally be clear from context. Generally, we're working with it when we are working with other vectors whose lengths we have specified. And so we just assume it, if it's being included in a sum like I have here, that it has the same length as the vector that it is being added to. But I think, again, that tends to be fairly clear from context. All right, so now we have a bunch of properties concerning vector addition and scalar multiplication. I just want to quickly run through these, discuss them a little bit, discuss why they're true, and then we will move on in this video. So first things first, if I have two vectors u and v, I can add them in any order I want. That is the commutative property of addition. That is u plus v is equal to v plus u. Next, if I have the sum of three vectors, so here u, v, and w, I can also add those three vectors. I can I like to think of this property as the property that I can either do u plus v and then add that to w, or do v plus w and then add that to u. Relating this back to real numbers, because again, most of these sort of mirror what happens with actual numbers. If I have 1 plus 2 plus 3, right, I could do 1 plus 2 is equal to 3 and say, well, 1 plus 2 plus 3 is equal to 3 plus 3. Or I could do 1 plus 2 plus 3 is equal to 1 plus 5. And so notice that would sort of mirror what's going on here, that if I'm adding three things together, I can add the first two together and then add it to the last, or add the last two and then add it to the first. Number 3, anything plus the 0 vector is always just equal to itself. Again, mirrors exactly. Whenever I'm adding 0 to anything, I should get that thing back. Number 4, so usually we'll express this vector negative u as the vector negative 1 times u. And so what this is saying is if I add u plus negative u, which is equal to u plus negative 1 times u, I get the 0 vector. Sometimes we'll also just express this as u minus u. So again, mirroring what happens with real numbers. All right, so now some scalar multiplication properties. I can distribute scalars across sums of vectors, and so that's what this is saying. So that is c times u plus v. I can distribute the c and say cu plus cv. I can distribute vectors across sums of scalars. So here I've got the sum of two scalars, c and d, times u, and I can distribute u through that sum. If I've got two scalars times a vector, it doesn't matter which order I do that in. So here I've got c times quantity d times u, or I can just multiply the two scalars together and then multiply them by the vector. Lastly, if I multiply 1 by any vector, I just return that vector. So notice properties 3 and 1 are somewhat similar in the sense that they deal with some sort of vector operation and returning the same vector. So here, sometimes we'll refer to 0 as the additive identity. That is, if I add the 0 vector to anything, I get that thing back. Sometimes we'll refer to 1 as the multiplicative identity, because if I multiply 1 by any vector, I get that same vector back. So like I said, most of these properties I feel are fairly intuitive in that they mirror how addition and multiplication works for real numbers. Often throughout the course, we will be using these properties without really referencing them, but sometimes it will help to remember that we do have these properties guaranteed for vectors of length n. All right, so sort of switching gears now. Let's say I had a set of p vectors, v1 through vp, in Rn. So these are all vectors of length n. And suppose I had scalars c1 through cp. Now let's say I have a vector y that is equal to the following sum: c1 times v1 plus c2 times v2 plus cp times vp. So here y is written as this sum of these vectors v1 through vp, where I multiply each vector by the corresponding indexed scalar. Then we say that y is a linear combination of these vectors. So the definition, or the term linear combination, I think comes from sort of the idea that we're combining these p vectors in order to create this new vector y. Right, and so you can imagine we're trying to find the correct set of weights so that if we add all of these vectors weighted by these scalars c1 through cp together, I can sort of create y. And so a question we will be asking and answering a lot in both linear algebra and in a lot of areas of math and science is the question of whether or not a vector y can be written as a linear combination of a set of vectors. So that will be like a central question we want to solve all the time in a lot of different forms in linear algebra. So I want to sort of look at a more discrete example of what that looks like. And so first off, I want to show that the following vector, 1, 3, 1, can be written as a linear combination of the following two vectors, 1, 2, 3, and 1, 1, 5. So I want to show that the vector 1, 3, 1 can be written as a linear combination of 1, 2, 3, and 1, 1, 5. So mirroring this back to the definition, so if I'm relating this sort of concrete example back to the definition, this would be my y vector in this definition. So 1, 3, 1 would be my y vector. 1, 2, 3 would be, say, vector v1, and 1, 1, 5 would be vector v2. And of course here p would just equal 2, and then I have two vectors. And so what I want are scalars c1 and c2, so that 1, 3, 1 is equal to c1 times 1, 2, 3 plus c2 times 1, 1, 5. And I think if we let c1 equal 2 and c2 equal -1, then we've got a valid set of scalars. And so we'll verify that here. So I've got 2 times 1, 2, 3 plus -1 times 1, 1, 5. So given how scalar multiplication works, this is equal to 2, 4, 6 minus 1, 1, 5. And so notice if we were to do the subtraction across, 2 minus 1 is 1, 4 minus 1 is 3, 6 minus 5 is 1. And so sure enough, 1, 3, 1 can be written as a linear combination of v1 and v2 because I could find suitable scalars that combine these two vectors v1 and v2 to give me y. And again, a very central question will always be like, when can I find a vector that can be written as a linear combination of these two vectors? And it turns out actually just with these two vectors, I could potentially find a vector of length 3 that couldn't be written as a linear combination of these two vectors. So actually, if you want to convince yourself of that, just sort of experiment with vectors of length 3. Try and sort of figure it out. One thing you'll find is that it's very hard. That if you don't know these scalars beforehand, it's almost impossible sometimes to find the correct set of scalars to make everything work. So, let's say we wanted to answer this question, can a vector be written as a linear combination of some set of vectors, and we didn't already know the correct set of scalars to pick beforehand? How could we answer that question? Well, I claim that we've actually seen this question asked in a slightly different way than I just asked it now. So what that means is that the question of can a vector be written as a linear combination of other vectors is a question that we've already asked and answered. We just don't know it yet. So let's go back a section or two and let's solve some systems of equations. So I'm going to let x1 plus 2x2 equals 7. Minus 2x1 plus 5x2 equals 4. And negative 5 times x1 plus 6 times x2 equals -3. Be a system of equations and so remember, a solution to this system of equations was an assignment of the variables x1 and x2 that satisfied all these equations, right? So a solution gave two numbers, and for now we'll just call them, for no particular convenient reasons, C1 and C2, such that x1 equals C1 and x2 equals C2, satisfied each equation. All right, so if we had a solution to this linear system, then each equation being satisfied meant, again, I had this sort of definitive assignment of x1 equals blank, x2 equals blank, each equation satisfied. But so notice, if this is a solution, then the following vector equation is also a valid equation. So what I've done here is I've created a vector for each one of my two variables, x1 and x2, where notice these are sort of the vectors of coefficients attached to each variable. So x1, 1, negative 2, negative 5, x2, 2, 5, 6. And then on the right side of the equal sign, I've made a vector for all of the coefficients there. And so notice, if equation 1 is satisfied, then 1 times x1 plus 2 times x2 is equal to 7. And so C1 and C2 are a solution. Well, then C1 times 1 plus C2 times 2 is equal to 7. And we can just keep doing that, where now the second entries in all of these vectors represent equation 2, and the third entry in all of these vectors represent equation 3. And so solving a system of equations is equivalent to asking, is this vector 7, 4, 3, a linear combination of these two vectors? We can also flip that around. If I give you a set of vectors and ask, is, say, this vector a linear combination of this set, we can set up a corresponding system of equations. And remember, we have a way now to solve a system of equations. So I want to wrap up with one example of that, how we might solve a problem like this, especially when it is worded now in the language of vectors. And so what we want to do is just determine if the vector b, that will be given in a second, this vector 2, negative 1, 6, is a linear combination of the following three vectors. A1 equal to negative 1, positive 1. So A1 equal to positive 1, negative 2, 0. A2 equals 0, 1, 2. And A3 equals 5, negative 6, 8. And so remember, we want, if this is going to be, so if B is going to be a linear combination of these three vectors, scalars C1, C2, and C3, such that C1 times A1 plus C2 times A2 plus C3 times A3 is equal to B. And so what we want to solve for are these three scalars. So given this, it is equivalent to solve the following systems of equations. So I'll write out the system of equations, and then we can solve it. So it is equivalent to solve x1 plus 0x2 plus 5x3 equals 2, negative 2x1 plus x2 plus negative 6x3 equals negative 1, and finally 0 times x1 plus 2x2 2 plus 8x3 is equal to 6. Right? And this is because, again, as we saw, I can just sort of translate these vectors to being coefficients attached to my variables in this system of equations. But we know how to solve this system of equations, right? We can set up an augmented matrix and reduce it to reduced row echelon form. So the augmented matrix corresponding to the system is the following. And so notice as I'm doing this that as you're solving these vector equations on your own, you can actually skip this step because notice that the columns of this matrix correspond to the ordered vectors in this equation, right? So column 1 is actually equal to vector A1, column 2 is vector A2, column 3 is vector A3, and the last column is the vector B. So whatever solution this gives us for x1, x2, x3, we're going to match up with C1, C2, C3, and that will be the solution that gives me a linear combination. If this system of equations does not have a solution, then we would conclude that B cannot be written as a linear combination of these three vectors. So let's row reduce this matrix. So first I'm going to do 2 row 1 plus row 2 and replace row 2. And next I'm going to do -2 row 2 plus row 3 and replace row 3. And I think after this step, I'm done. So just a quick recall to sections 1.1/1.2. This is in reduced row echelon form. All of my leading entries are 1s. All of the 0 rows are at the bottom of the matrix. And all of the leading 1s are by themselves in the column along with other 0s. So remember, this corresponds to the system of equations x1 plus 5x3 is equal to 2, and x2 plus 4x3 is equal to 3. Right? So again, I just associate each column with a variable. Now, because x3 does not correspond to a leading 1, x3 is a free variable. And this means in this solution, I can pick any value I want for x3. So what that means is I can let x3 be any value I want, and x1, x2 will be fixed based off of that. So in order to find the solution, I'm just going to let x3 be 1. That means that x2 is equal to 3 minus 4, so x2 is equal to -1. x1 is equal to 2 minus 5, and so x1 is equal to -3. And notice if I replace now -3 times a1 plus -1 times a2 plus 1 times a3. Well, let's see what we get and double check to make sure this actually works. So -3 times a1 is equal to the vector -3, 6, 0, minus a2, 0, 1, 2, right? And notice this is because I'm doing plus -1 times a2. Now I just want to add 1 times a3, and so that should just return a3. All right? And so if I did everything correctly, I get -3 plus 5 is equal to 2. 6 minus 1 minus 6 is equal to negative 1, and 0 minus 2 plus 8 is equal to 6. And so sure enough, using this set of weights, I can write these three vector, or I can write B as a linear combination of A1, A2, and A3. And so again, to sort of just summarize, had the corresponding linear system and augmented matrix that I row reduced gave me no solution back, that would imply that B could not be written as a linear combination of these three vectors. But any solution I get to the corresponding system that I had set up will correspond to a set of weights, C1, C2, C3, that I can place on A1, A2, A3 in order to write these vectors as a linear combination to get B. So it turns out solving vector equations is equivalent to solving systems of equations, which is equivalent to row reducing matrices.